Uh, 5.4. The first fundamental theorem of calculus. Yeah, integration is the B part. You know, I said this is AB. The A is the derivative. The B is the integration part. Well, no, then it goes BC. It continues with integration. It goes on to. I'll let you figure it out here. All right. What do we have this picture? The area under the curve. Bam. That's nice. Okay. So. Here is my favorite calculus textbook quote of all time. Yeah, I didn't write that. Yeah. If you were being sent to a distract and could take only one equation with you, this might as well be your choice. I don't know, just, this is actually so much simpler than it looks. It's crazy.
You always say that.
No, well, because I get through it and you're like, you know what, you're right. And then you get home and you're like, I couldn't do it when you weren't there. And I'm like, that'd be crazy. It is, I know. All right? If you were being sent to a desert island and could only take one equation with you, it would be, what does this d over tx represent? Derivative. What does that represent? They're opposites, right? Okay? Integration. Derivative and integration, they're opposites, they can cancel. So f of t would just be f of x. It's just the equation itself. Okay? It's just the equation itself. Now,
I don't get it.
that's why we have notes on it, so you can better understand it. All right? The fundamental theorem of calculus part 1, because there is a part 2. Okay? If f is continuous on some sort of interval from a to b, then the function f of x equals the integration from x to a of the function f of t. Okay? Okay? Not only does this hold to be true, just follow. Don't just try and understand it right now. Just follow. Okay? And as we start doing some of these problems, we'll be like, oh, that's really, why didn't you just explain it like that? I'm trying. So, if it's continuous, it also has a derivative at every point, right? If it's continuous, it has a derivative at every point. Which means, this is what I just showed you. Stop it. Why don't you guys start complaining? I can take, because, see, this is capital. If I want to take the derivative of this, I got to take the derivative of this, don't I? So, that's saying just take the derivative of what's up here, the integration. That's the same thing as it's taking the derivative of the capital function. Okay? They're saying if you can take and integrate a function that's continuous at every point, it has a derivative at every point. And if you can take the derivative of an integration, don't the derivative and integration just cancel? So this is just this. Nothing really changed except the t and the x, right? Let me show you, children. And where do you see an x here before you even get anywhere else? Where do you see an x? Anywhere. Here. What position is the x in here? Not just here, not just f of x. The upper bound. So it's the same function, you just put the upper bound of x in for t, and that's it. Because you can't just cancel this out, let's see the derivative of the equation. Alright, so here we go. So let's really think about this, and I really just walk you through it right now. This is taking the derivative of an integral. So what do you know about this? What are derivatives and integrals of each other? They're opposites. Like addition and subtraction are opposite. Like multiplication and division are opposite. They cancel each other out. Okay? All right. Find df dx. Let's apply this theorem using common sense. Okay, so now we're past the notation in the book. Let's actually just look at this and use some common sense, shall we? Okay, let's integrate. See what we got right here? We're going to take the derivative of the integration of 3t squared. Okay, so first let's start by just integrating 3t squared. What's the integration of 3t squared? It's t cubed. Don't I add 1 to the exponent, then divide by that new exponent? 2 plus 1. That's 3t cubed over 3. It's gone. So right now, t cubed is the integration of 3t squared dt, right? Which means this can just substitute in the parentheses there. So now let's take the derivative. Okay, now we're doing this, taking the derivative of t cubed, and you get, and then, you know, dt times or whatever. I mean, it's just this. But what about this t and x thing? What about this t and x thing? Okay? If you're going to take a derivative with respect to x, all they're telling you to do is just change this variable. So next. That's all. That's all. There's no rhyme or reason besides, okay, we're taking a derivative with respect to x now. So your variable should now be an x instead of a t. Well, it can be. The answer is not 3t squared, it's 3x squared. Okay. All right. Ready? I love your eyes. Okay, so the first fundamental theorem we got. There. Take the derivative of the integral. Okay? That's d over dx, you know, in front of the integral. From x to a. Okay? The derivative matches the upper limit of the integration. What's that mean? The variable for your derivative should match the upper limit, or the upper bound. Could also be an x. Because if you notice through this whole thing, the only place the t was here. This is going to t, it's an x. This is going to t, it's an x. Because when we do this, we do f of x and 4t minus f of a, whatever. A is going to be a constant. That'll wipe out. Boom. What's the derivative of a constant? Yeah. So after you integrate, and then I take the derivative of each, the derivative of each, the derivative of a constant is 0. So that's why that t turns to an x. You have to understand it, you're just going to make sure you put x in for the t. All right? The lower limit, as I just stated, is always a constant. That's how it goes away. Because when you take the derivative of a constant, it's 0. See? So let me walk you through that one more time, slowly, because Alex asked, does it really matter if it's a t or an x? No, you don't have to. I mean, if it's only going to confuse you more, then don't. For those of you that are curious, I'm going to show you right now. I'm going to integrate this function right here from my upper bound x to my lower bound a. That means I take f of x minus f of a. Don't forget a is a constant, correct? Correct. Now, after I integrate, I got to take the derivative. And if I take the derivative of a string of expressions, it's like taking the derivative of each one individually, right? The derivative of this, and the derivative of this. The derivative of any constant, 0, because a is a constant. So really, you just have this left, okay? All right. These are not meant to trick you. Look at these for about 5 seconds and tell me what you think the answers are. No. Some people say something's different. Some people say something's the same. All right, again, what do you think? What do you think this is going to end up being? Stop it! Then I got to take the derivative of it. So these cancel, and my x just goes. So that's just cosine of x. What do you think is going to happen here when these cancel? That's it. That's it.
Oh, but wait, there's more.
Okay. So, I'll address that in a second. Now, why do these work? 0 is a constant. Negative pi, that's a constant. That's 3.14. It doesn't change. They're constants. So when you take the derivative of those, boom, zeros. And the derivative of the integration will cancel each other out. So here's like a cosine with the x. Yeah. So what obvious questions should you have? If looking at this, what are you going to ask me? But, Visca, what if? Okay, yeah, good. Nice. That's one of the questions you should ask. I'm not going to answer it. No, yes, I am. Okay, so here's a 3 that I come up with. What if the upper limit is the constant, and the lower limit is the variable? Yes. By doing what?
By making it negative.
Negating the integration flips the bounds, right? Okay, what if the derivative variable and the upper limit do not match? Like t over dx. The upper limit is an x. Maybe say something else. Okay. And what if there is no constant for either limit? What if it's like an x on top and some sort of other variable type on the bottom? Well, I'm glad you all asked those questions because we're going to answer each and every one with an example. Bam! What if the upper limit is the constant and the lower limit is the variable? See, the 5 should be on the bottom and the x should be on the top. That's how this whole thing works. And Tommy and Xavier, you guys were both right. Remember, negating the integral will flip the upper and lower limits. Okay? So I'm going to rewrite this all nice and neat. And I'll say d dx of the negation of my integral, and now I can flip those limits. Now the x is on top and the 5 is on the bottom. Of 3t sine of t dt. So now, apply what we just learned. What's that going to equal? 3x sine of x. Negative. Don't forget, the negation has to be there because the sign's flipped. The bound's flipped, excuse me. That's it. It's a crazy circus, isn't it? Question. If you know what you're doing, yes. If you know that's the answer, yes, you can just write it. Okay? Well, there's always one. Okay? What if the derivative variable and upper limit do not match? Like, we had t over dx. This isn't an x, it's an x squared. It means the chain rule means times the derivative of, right? So, I have this right here. If I were to do this without any sort of chain rule, what would happen? What would it equal? Well, no, cosines, these cancel. Well, it's going to be x squared, right? Times the derivative of whatever was just put into here. So that's 2x cosine of x squared. If you want to look at it this way, you can. You ready? Chain rule or u sub. Let u equal x squared. So du equals 2x dx, or in this case dt, whatever. So now, if I were to take the derivative of that function right there, d over dx, the integration from u to 0, for the cosine of u, du. That would just be the cosine of u, which is x squared, right? But now this is going to go away. What is that? I just say, like, you know what trig is? We take the derivative, and then there's always times the derivative of what's on the inside, right? You always got to take that into effect. And that's all that is for chain rule. You take the derivative or integration, then times the derivative of the inside. In this case, the derivative and integration cancel, but we still can't forget about that inside. All right? Not too complicated, is it? Doesn't think so. All right, and what if there is no constant for either limit? We split the integral into two parts. No, it may be, but that might be complicated. I'm just going to say, I'm going to take the derivative of the integration from x squared to 0 of 1 over t plus, or excuse me, 1 over 2 plus e to the t dt plus the integration from 0 to 2x. See what I'm saying? Of 1 over 2 plus e to the t dt. Why do I do that? Well, if I want to take the integration from like 0 to 5, I can take the integration from 0 to 3 and add that to the integration from 3 to 5. I do the same thing. Let me give you a visual. Because some of you are looking at me like you're trying to get it, you're almost there. From 1 to 5. If I want to find the area under the curve, which is the integration, right? I can just take the integration from 1 to 5. That's this whole area, absolutely. Or if I wanted to break it up for whatever reason, I can go from 1 to 3, that integration, and add it to the integration of 3 to 5, or 5 to 3. I can do that. It's the same thing. That's all we're doing, split it up. Now we have a constant in each. But what's the problem with the second one? So how do we switch that? So I'm going to rewrite this, because in order to use our first fundamental theorem, this one's okay. It's the integration from x squared to 0, 1 over 2 plus, e to the t dt. I'm going to change it to a minus. How come? Because now I'm going to flip the bounds. Now I'm going to put the 2x on top and the 0 on the bottom. This is just one of those things where we're using two of the sections. 1 over 2 plus e to the t dt. And I'm going to take the derivative of it off. Which means the derivative and integration are going to cancel, aren't they? The derivative and integration is going to cancel. So this will cancel with this and this. And what am I left with here? What's this first thing going to end up becoming? 1 over 2 plus e to the x squared times 2x. Remember, if it's not x, a chain rule. Plug it in and take the derivative of it. Just like here. Wasn't this x squared? We put an x squared times the derivative of x squared. Here, we had to put an x squared times the derivative of x squared. All this minus. What do we got in the second one? 1 over 2 plus e to the what? 2x times 2. And if I wanted to clean that up, I put these on the tops of the fractions. Okay? I would say my final answer would be 2x over 2 plus e to the x squared minus 2 all over 2 plus e to the 2x. If we couldn't use that first fundamental theorem of calculus, that would be very difficult to do. There we go. There we go. Okay. All right, the fundamental theorem of calculus part 2. If f is continuous at every point on A and B, and if f is any antiderivative of f on A to B, then this is what we have anyways, isn't it? Well, we have an integration from B to A. We need to put those in and subtract them. That's where this leads. All right? So keep in mind, this is just a funky way they'll write it in the textbook, okay? They won't say that, okay, this is the integration of f of little f of x. And this is they'll say that the integration of f of x will represent a capital F. So here, you take the integration, which is the capital F, and you just plug your b value into it, because that's your upper bound. And you subtract the integration again, which is capital F, when you put an a in. That's how they write it. They say capital F is the antiderivative. So when I take the antiderivative of this, I have to get a capital F. So this was 3t squared. This would be t cubed. And then I put my b bound in there. And subtract t cubed when I put my a bound. That's what we learned what integration does. That's where it all leads. Now I have a deeper understanding, not that you care, but exactly. All right, I think that is it, is it not? That is it. So there's the homework, and we will start to go over some problems now in class. I'll do some problems.